Okay, next speaker is Fabrizio Martino from University of Palermo. Are you ready?
Hi everybody. Yes, I'm ready.
Okay.
Ciao a tutti.
The title is Differential Identities and Polynomial Growth of the Codimensions.
Okay, I will share my screen.
Yes.
Okay. So please give me feedback.
Yes, it's done.
Okay, I think it's
Yes.
working. This. Okay. This was my door. There's a lot of wind. Today is a windy day, so but nobody. Okay. So guys, first, of course, I want to thank the organizers for this opportunity. In particular, I want to thank Artyom that invited me to talk today here. And what is the main topic of my talk? The main topic of my talk, as you can see, is the polynomial growth of the codimensions of the algebras with derivation. So it's the continuation.
Fabrizio, your microphone
Yes.
is not working.
Oh. It's not working. That's weird. Can you hear me?
Oh, yes, I can. I don't know.
I do as well.
Okay, it's okay for me, but I don't know if there is some problem.
I don't know. Maybe it's a problem when I present my slides. Let's take another.
Oh, it is fine when you present. It is fine.
Yeah. So
Yeah.
now you can hear me.
Everything's
Sure.
fine. Keep going.
Okay. So I talk about the polynomial growth of the codimensions of algebras with derivation. So it's the continuation of the talk of Carla. So I will not give the same definitions. I will present, just briefly remind the basic stuff, but I assume that everybody here remember what Carla said. So the focus of the first part of this presentation is about the so-called minimal varieties and the classification problem in terms of growth of the codimension of a given algebra. So let's start. Recall very quickly that if we have a variety of associative PI-algebras in characteristics 0, all the works here is in characteristics 0, then you know that the space of multilinear polynomials, Pn, has a dimension as n factorial. So a priori, the codimension sequence is bounded by the factorial, but Regev in 1972 proved that if you have a PI algebra, or there is the same, a variety of PI algebras, as such a sequence of codimensions exponentially bounded. So there exists integers d and k such that we have this inequality. The codimensions grows as d to the n. Very well. Then what happened? Happens that Kemmer in 1979 proved that yes, the codimension sequence is polynomial, is exponentially bounded, but is also it can be also polynomially bounded. So there is no intermediate growth among the polynomial one and the exponential one, and he gave also a criteria in order to know when the codimension sequence grows polynomially. In fact, he proved that such such sequence grows polynomially if and only if the infinite Grassmann algebra E and the UT2, there is the 2 times 2 after triangular matrices, do not belong to the variety that we are studying. In this case, the codimension sequence grows polynomially and vice versa. Very well, so there are two families of varieties. There are the family of the varieties with exponential growth of the codimensions, and in particular, then we have the varieties of polynomial growth of the codimensions. So I I want to talk about this classification problem, but what does it mean to give a classification of the varieties on the codimension sequence? Well, first we have to establish a condition for which two varieties are equivalent. So I will say from now till the end of the talk that two varieties are PI equivalent, or simply they are equivalent if and only if they have the same T ideals of identities. So we say they are PI equivalent. So if we want to give a classification of the varieties with exponential growth of the codimension, this means to find a complete list of non-equivalent varieties, V1, V2, V3, etc., such that for all integer d, such varieties are the only one with the codimension that grows like d to the n. Similarly, if we talk about varieties with polynomial growth of the codimension sequence, for all k, for all integer k, we want to a priori find a complete list of non-equivalent varieties with the property that the codimension sequences are approximated by n to the k. These problems are very far from being solved, and I want to present you, just for an example, we could say a partial result about, in this case, about the exponential growth. The corresponding classification problem was almost solved just for d equal to 2. That means that we know a criteria in order to have varieties of exponential growth like 2 to the n, but we do not know what happens when the exponential growth is greater than 2. In this setting, Jambrou and Zaitsev in 2000 proved the following. They proved that the codimension sequence is approximated like to 2 to the n if and only if the variety that we are studying has inside a copy of UT2 or the Grassmann algebra, and such variety does not hasn't a list of algebras that have exponent greater to 3. There is a list of algebra that they established. You have to delete this algebra from the variety. You have to put into this variety the Grassmann algebra or UT2, and then you have the codimension sequence that grows like 2 to the n. A similar result was achieved for graded algebras in 2019 for me and Ninni Antoniopoulou. We proved that in case of graded algebras, so we have a variety of graded algebras, the codimension sequence grows like 2 to the n if and only if you have to delete some algebras, some graded algebras. In this case, in the variety, you have to have at least one among the commutative algebra f times f or UT2. These algebras have trivial grading. Or similarly, you have to put UT2 with grading that you can see here. So this is the natural grading of UT2. So the even part, the part of the unit element of the group is formed by the diagonal matrices. And the other part is formed by the linear span of the element E12. So you have to have UT2 with this grading, or the Grassmann algebra with the trivial grading, or, once more, the Grassmann algebra with its super grading, natural super grading, Z2 grading. So we have the zero part that is formed by the even monomials in the generators, and the even part that is formed by the odd monomials. Odd monomials, I mean monomials in the generators that have odd length. Very well. And just like another example, we can talk about algebras with involution. In 2020, Gianbruno and Lamattina proved a similar result for algebras with involution. So they took a variety of algebra with involutions, and they proved that the codimension sequence grows as 2 to the n if and only if you have always to delete some algebras, some suitable algebras, and then you have to find into the varieties these two algebras with involution. The commutative algebra f times f plus the exchange involution, there is the following. You have an element of f times f, f plus f, the exchange involution just change the places of a and b. Or you have to find inside the variety this algebra M, introduced, if I am not wrong, by Mishenko, I think, but I can be wrong. And with the reflection involution. The reflection involution is the involution that reflects each matrices along the secondary diagonal. So you have to find into the variety these two algebras in order, at least one of these two algebra, in order to have a codimension sequence that grows like 2 to the n. And we are talking just of d equal to 2, and we have no information about d equal to 3, d equal to 4. That it's a very open problem. So if we, very well, before talk about the polynomial growth, all the algebras that appeared in the previous results, so the result of ordinary identities, graded, or identities with involution, are the so-called algebras that generate varieties of almost polynomial growth. We briefly recall that a variety is called of almost polynomial growth if its codimension sequence grows exponentially, like d to the n for some d, but with the property that any subvariety, any proper subvariety, has the codimension sequence that is polynomially bounded, so grows like n to the k for some k. The classification of the variety of almost polynomial growth was done by Kemmer in 1979, concerning ordinary identities, so algebras without any additional structure. By Angela Valenti in 2011, in the setting of graded algebras, if I'm not wrong, with the finite abelian group. And concerning algebras with involution, this classification was done by Gianbruno and Mishenko in 2001. So a variety of almost polynomial growth is something that is exponential, of course, but it is very close to the polynomial growth. So there are a subfamily of the exponential varieties, the varieties of exponential growth, that is of very interest. So, talking about the polynomial growth, recall, we would like to find a complete list of non-equivalent varieties such that for any k, all these varieties are the only one with the codimension sequence that grows like n to the k. In order to show how difficult it is to resolve in the general case this problem, this classification problem, I will show you just a result by Oliveira and Vieira that proved in 2021, was proved in 2021, in which they take varieties of unitary algebras, so they worked with algebras with unit element, and they classified, in the sense of the classification that we talked before, the varieties of polynomial growth with the codimension that grows as n to 4. And in this classification, the classification that they obtained, they proved that, you know, the variety has polynomial growth like n to the 4 if and only if it's generated by one of the following. I don't want to say you which algebra is G4, N5, M, K, the direct sum, and among these algebras. The idea is that we are talking about a small polynomial growth, n to the 4. And even for this small polynomial growth, the situation is very complicated, because we have at least 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, more than 10 algebras in order to classify the varieties of polynomial growth n to the 4. So just for give you the idea that this problem is very far from being solved. Very well. So what we are doing? We can be helped by the definition of the so-called minimal varieties of polynomial growth. Now I have to make some remark here, because there are in the theory of polynomial identities, there are the definition of minimal variety of exponential growth. This definition is not the one that we are using here. So I will say minimal variety or minimal algebra in order to denote a variety or an algebra that satisfies this condition. So we have to make no confusion among the two definitions that sometimes can arise. So a minimal variety of polynomial growth is a variety which codimension sequence grows polynomially, like n to the k, with the property that any subvariety, of course, the codimension sequence of any proper subvariety grows polynomially. This is a direct consequence of the definition of the codimension sequence. But the variety V is called minimal if happens this fact here. The integer t, n to t, is strictly less than k. In this case, V is called minimal. Minimal in the sense that is the smallest variety with polynomial growth n to the k in this sense. So in order to simplify the notation, I will say also that an algebra is called minimal, but in my sense, an algebra is called minimal if it generates a minimal variety. Maybe this is an abuse of notation, but it's very simple for me to say algebra, minimal algebra, instead of an algebra that generates a minimal variety. It's very complicated for me to say all these sentences. So we are agree now that an algebra is called minimal if generates a minimal variety, just this. So why we are interested in minimal varieties? Because it seems, empirically speaking, that minimal varieties are like the building blocks of the general varieties of polynomial growth. In fact, this conjecture seems to be true, that if you have a variety, you have the algebra that generates such variety, you have the algebra, the codimension sequence that grows polynomially, then the algebra that generates the variety is equivalent in the sense that we were talking before, is equivalent to a direct sum of minimal varieties plus a nilpotent algebra. Nilpotent algebra means codimension sequence that is eventually 0. So in terms of asymptotic behavior, the nilpotent algebra gives no information. So the important thing is this part of the direct sum. It seems that you have to classify, if you are able to classify all the minimal varieties, then in order to get an algebra of polynomial growth of the codimension sequence, you have just to sum in all possible ways the minimal algebras that you found before, plus an nilpotent algebra. It seems to be true. What can we do? Just for give you also the idea of how hard it is to solve the general problem. So just not looking for minimal varieties, but to solve the whole problem of the classification in case of polynomial growth. there is this result by Gianbruno Lamattina and Zaitsev in 2014. In the case of unitary algebras, they classify all minimal varieties of polynomial growth with the codimension that grows at most like for n to the 4. And they prove that there exists a finite number of them. If I'm not wrong, they classify the varieties in terms of T-ideals of identities. And they gave a recipe for constructing minimum varieties of growth greater than 4, so n to the 5, n to the 6, and so on. But they also show that is very interesting that in this case, the number of non-equivalent minimal varieties grows like the cardinality of the base field. So if you have a base field that is like with like the real numbers of the complex number, you have a lot of minimal varieties, non-equivalent minimal varieties. And of course, this in case of unitary algebra. I always found this theorem very interesting because they use the co-character of the variety. They give some condition on the co-character sequence of the variety in order to be minimal. And they work with such condition in order to construct a minimal variety. It's very interesting, I think. Very well, but why we do believe that the previous conjecture is true? We do believe that the previous conjecture is true because, empirically speaking, we have some example, and these examples are just in the setting of the variety of almost polynomial growth. So we recall a variety is called of almost polynomial growth if the codimension sequence is exponentially bounded, but for any proper subvariety, the codimension sequence grows polynomially. So in case of almost polynomial growth varieties, we are able to solve the classification problem of the polynomial growth of the codimension sequence because we do know how to completely classify these subvarieties inside an almost polynomial growth variety. For any k, we are able to construct a T-ideal, an algebra, or an algebra that generates a variety of polynomial growth n to the k inside the variety of almost polynomial growth. And it seems true that the conjecture holds. So it turns out that any subvariety is generated by a direct sum of minimal algebras plus, of course, an nilpotent algebra. So I want to show you now the classification problem in case of almost polynomial growth variety for ordinary algebras, graded algebras, and algebras with involution. Then I will present the result of my work with Carla Rizzo concerning algebras with derivation. So let's start talking about ordinary polynomial identities. Recall that in this case we have just two varieties of almost polynomial growth. There are the varieties generated by UT2 and the infinite dimensional Grassmann algebra. So Kemmer in 1979 considered such subalgebras that belong to the variety generated by UT2. So you have this element H, and you can consider such three algebras. I just want to point out that just the first algebra, NK, is an algebra with unit element. The other one, AK and AK star, are algebras without unit. Just for visualize the situation, I put down here an example. There are two algebras, N4 and A4. There are subalgebras of UT4, the 4 times 4 upper triangular matrix algebra. The idea of N4, NK in general, is the following. You have on the main diagonal, of course, the unit element, so the same element on the main diagonal. The first row of these algebras of type nk is free. So you can have all the elements you want on the just on the first row, because on the secondary diagonals, you know, here there's just n4. If I plotted n5, you have just another element here equal to e. So in the other diagonals, the elements are repeated. So here we have an e, we have another e. Of course, we have just an f because we are considered n4. But if we consider n5, down there we will have another f and so on. So the other diagonals are with the same, contains the same elements. The same idea is behind A4. The only difference is that you don't have the unit element, so you have just this element a priori different from 0 on the main diagonal, and then you have the same situation. So the first row is free, and then on the other diagonals, you have the same elements that it is repeating. So Kemmer proved that Kemmer proved that the almost polynomial growth varieties are generated by E and UT2. Daniela La Mattina in 2007 proved that the classification of the subvariety contained in the variety generated by UT2, solving the problem of the classification in case of polynomial growth. So if you have a subvariety of the variety generated by UT2, then A is equivalent to one of the following. Of course, UT2, the whole variety, and or just an nilpotent algebra, or these three algebras that we introduced, NK, AK star, or the direct sum in all possible way. I do not list all the possibilities, but the idea is that you take NK plus NK, and then you take NK plus AK star, and then you have to make all the possible combinations. And these one, AK, NK, and AK star, are the only minimal algebras inside the variety generated by UT2. She also classified the minimal varieties inside the variety generated by the Grassmann algebra by proving simply that in this case we have one minimal algebra that is the finite dimensional Grassmann algebra. So you take just 2k generators of the Grassmann algebra, you take, of course, why of course? You take also the unit element, and then you have a minimal algebra. And she proved that inside the variety generated by the Grassmann algebra, then you can have the Grassmann algebra, you can have the minimal algebra, so E to K, and then the nilpotent plus or a commutative algebra. She proved in the same paper this result. The situation is very, 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 very more complicated in case of algebras with grading, with group grading. In 2011 proved that in the almost polynomial growth varieties are just the following. So you have UT2 with a grading that can be also trivial. You have the Grassmann algebra with trivial grading. You have the Grassmann algebra with the Z2 grading. We call it the natural Z2 grading. And then you have the group algebra of the cyclic group of order P. So CP is the cyclic group of order P. P is a prime number. You have the group algebra, and then you put on the group algebra some grading that is indecised by H, that is an element of the group. So inside UT2 with any grading, the minimal varieties are the same algebra as before, NK, AK, and AK star, but with the same, with the grading induced by the elementary grading induced by this element. So you have the unit element and then G repeated K minus 1 times. Very well. Talking about the varieties generated by the Grassmann algebras, then it was proved that in case of trivial grading, of course, we have the previous case. So the only minimal algebra is E to K. In case of group of order and even number, then you have to consider an element of G that is of order 2, and then the Grassmann algebra, the finite dimensional Grassmann algebra, with the grading that is the natural Z2 grading. The difference is, of course, that here K can be also odd. It is not even. Can be also even, but it is not just only even. And to complete the information, inside, look at this result, inside the variety generated by the group algebra of cyclic group, this is the situation. Even here, I don't want to you know, I don't want to stop here for I don't know how many minutes, because is the idea that I want to show you. You have to take, in order to get a minimal algebra, the ring of polynomials in P-1 commutative variables. You have to put on it a grading. Then you have to make the quotient with the ideal generated by the variables to these parts of the composition of K into P-1 parts. It's a very complicated construction. It's very hard to prove this result, but Daniela in 2015 proved that classified the minimal varieties inside all such varieties, and then proved similar results. So in order to get polynomial growth, you have to properly combine all the minimal varieties you found. And just to present the result in the setting of involution, we have just two minimal varieties, we have just two almost polynomial growth varieties, the commutative algebra with exchange involution, in the algebra of, we call it the Mischenko algebra with reflection involution. In case of the commutative algebras, the only minimal varieties are generated by this commutative algebra. This commutative algebra is just a subalgebra of the K times K upper triangular matrices. We have the unit element, and then we just have the diagonals that are equal. So all the elements on the other diagonals are repeated with this involution. In case of Mischenko algebra, we have these minimal varieties. Of course, there are, we use the same, almost the same notation of the previous case, but we are considering different algebras. So for example, U3 and U3 or N3 are like direct sum of two algebras. Of course, they are not direct sum because we have the unit element, we have the first row and the last column that contains 3 elements, but this one that is repeating, and then we have the secondary diagonals with the same philosophy as before. So on the secondary diagonals, the elements are repeated. AK, A3 in this case, is the same. So the first row, the last column are 3, and then you don't have the unit elements. So we have just A in the place 1, 1, and KK, and then the secondary diagonals are repeated. We proved in 2016 that these algebras are the only minimal algebras inside the commutative variety, the variety generated by the commutative algebra and the variety generated by the Mischenko algebra. And then we proved that in case, if you want to get polynomial growth, we have to combine properly all the varieties. So I want, so in this moment, just to present the result in case of differential identities. And as we said, as I said before, I am assuming that you recall all the stuff that Carla said. So very quickly, you have UT2, all the derivation inner. These are the same slide of Carla, just with blue color. So the same information. I am not saying something new. In UT2, you can consider epsilon and delta. There are inner derivation induced by E11 and E12. This is the algebra. Then you can put on UT2 a trivial action, you know, just by take these applications. So from the Lie algebra to the derivation algebra, the application is the 0, 1. In this case, we say that L acts trivially on UT2. In case of epsilon, you can take the inner derivation induced by E11 and make the same work as before. I'm going fast because they are literally the same slides of Carla. And we recall that the differential identity, the T-ideal of differential identities in case of trivial action is generated by these polynomials. So for all derivation in the universal enveloping algebra of L, x to delta is a polynomial identity, and then this one, there is the ordinary polynomial identity of UT2. We recall that trivial action means ordinary polynomial identities. In case of epsilon, we have this situation. We have that the T-ideal of differential identities is generated by these polynomial identities that actually reflects the structure of the derivation algebra, of the Lie algebra, pardon, in this case, and these polynomial identity with derivation that tell us that you have a commutator, you can, the image of the commutator under epsilon is equal to make nothing, to have the commutator without any derivation in it. Very well. We do know the T-ideal of identities of UT2. There is this one. Gianbruno, Carla proved that in this case, the T-ideal of differential identities of UT2 with epsilon is the following. And also we have the information on the codimension sequence. You know, the exponent, as Carla said, is always equal to 2 in case of trivial action and in case of action with derivation induced by E11 with epsilon, actually. So, Kemmer proved that UT2 is almost polynomial growth, as almost polynomial growth. Also, Gianbruno, Carla proved that the variety generated by UT2 has almost polynomial growth. But also, she proved that the variety generated by delta, where delta is the inner derivation induced by E12, is not polynomial growth, has not polynomial growth, because inside this variety you can find UT2 epsilon. Actually, this is the reason for which this variety has not polynomial growth. So, up to equivalencies in finite dimensional case, you know, the UT2 and UT2 epsilon are the only L varieties of almost polynomial growth. So we work on these subvarieties. Actually, these subvarieties of UT2 with trivial action are the subvarieties of UT2 as ordinary algebra. So we did nothing. But we construct minimal varieties and also the subvarieties of UT2 with epsilon. And we took the same algebra as in the previous case, and K, AK, and AK star, and then we put on them a derivation that we call also epsilon in order to don't mess up the notation. There is the inner derivation induced by E11. But you know, you have to be careful because these derivations are not this derivation epsilon on NK, for example, is not the same derivation of UT2, because UT2, the epsilon UT2 is the inner derivation induced by E11, just like an element of UT2. Here, E11 is an element of NK, and so on. So we use the same notation, but they are not the same derivations. Of course, these are the only minimal algebras, and then we prove that in this case, in order to get the polynomial growth of each subvarieties, we have to properly sum all these minimal algebras that we found in the previous case. As a corollary, of course, we proved that the only minimal algebras inside the variety generated by ut2 with epsilon are these three, and u with epsilon, and k or nk star with epsilon. So we closed the problem. As Carla said, one of the most challenging problems was solve the the problem of the stability of the Wedderburn self-composition. But it turns out that in case of this variety, the Wedderburn self-composition was stable, so we found actually the algebras of the ordinary case just putting on that a derivation. So I thank you for your attention. Obrigado pela atenção, todo mundo. E my presentation ends here.
Okay, thank you. Comments, questions? Nothing? Okay, let's thank again Fabrizio. Thank you, Fabrizio.
Obrigado a vocês. Obrigado.
Okay, this is the last talk of the first part of today. So we have a break until 1:30. Yes, 1:30 p.m. Brazilian time, or 6:30 p.m. Italian time. So see you later.
Até mais.
Até mais.
See you soon.
Bye all.
Bye bye.
Bye bye.